In this lecture video, we're going to be looking at a variety of types of residual plots that are used for assessing the adequacy of a regression model. These plots help us identify potential violations of model assumptions. Now, there are two broad categories of types of plots that we'll be looking at. The first would be a normal probability plot of residuals, or some version of that. And these types of plots are used for checking the normality assumption of the error terms. Now, the other broad type of residual plot is a scatter plot of the residuals versus the fitted values, the y-hats, or we could look at scatter plots of the residuals versus an explanatory variable. Now, these types of residual plots are useful for identifying situations when there is non-constant variance. It can also be used for determining when the deterministic part of the model has not been specified correctly. We've left out a variable, for example, or we've not included a particular measured variable in the appropriate way. So maybe we've left out a quadratic term, but the quadratic term is actually needed to explain variability in the response. And the other use for this type of residual plot is to look for potential outliers in the data. Now, before we look at this first type of residual plot, a normal probability plot, what I want to do is take a look at a SAS program that I've created. The error terms are assumed to be normally distributed. And if that's the case, then the residuals will also be normally distributed. And a normal probability plot is constructed in such a way that it can help us to visually identify when the residuals are not normally distributed. Now, it's not foolproof because it can be very difficult, especially in small samples, to distinguish between situations when the residuals are normally distributed and when they're not. And so in order to give us a feel for what these normal probability plots might look like for normally distributed random variables of different sample sizes, I've created a program here. And what I want to do is to run this program. And what it's going to do is it's going to generate samples of standard normal random variates for a variety of sample sizes, ranging from 5 up to 500, and then construct the following types of plots for these samples. Now, we're going to be looking at probability plots, but we're also going to be looking at histograms of those random variables. We'll be looking at what are called empirical CDFs. And then finally, we'll also be looking at probability plots. Now, theoretically, we could use all three of these types of plots of random variables to determine whether or not the random variables are normally distributed, but it can be difficult. And again, I said, it's not foolproof. And that's why we want to look at this so that we can get a feel for this. So let's go ahead and scroll down. And let me see here. It looks like I said I was going to use sample sizes up to 500, so I better include that. And so here what I'm going to do is I'm going to generate normally distributed random variables, in particular standard normal random variables. And then I'm going to invoke proc univariate, and I'm going to construct a histogram, a CDF plot, a probability plot, and a PP plot, which is a version of a probability plot that is available in SAS. And then I'm going to use the ODS select statement to select just the plots that I'm creating. I don't really need to see all the summary statistics and so forth that proc univariate generates. And what I'm going to do, I'm going to, for each sample size, samples of size 5, 10, 25, 50, 75, 100, and 500. For each one of those sample sizes, I'm going to generate 3 samples. All right, and then I'll be creating these plots for each combination of sample size and sample number. All right, so let's go ahead and run this. Okay, so you can see that took a little bit to run. And so let me go back up here to the very top of the output. So here I'm looking at samples of size 5, and I've got 3 of those samples. And for each of these samples, I'm going to, I've constructed a histogram. And obviously, with a sample as small as 5, the histogram is going to be fairly sparse and not very interesting and not very informative. But with this histogram, I've superimposed over the histogram a normal curve that has the same mean and standard deviation as the sample. And so what we want to do in looking at this histogram is to see, does the histogram look like that normal curve that's superimposed or not? And if it looks very much different than that normal curve, then that might lead us to suspect that the underlying data are not normal. Now, we know that the data that we're looking at is normally distributed because we constructed it. We generated that data. And so what we're looking for here is to see how much variation, how much deviation can we expect in these various kinds of plots from the theoretical normal distribution, whether it be the theoretical PDF in this plot or the theoretical CDF in, for example, in the next plot. So here is the CDF plot, the empirical CDF plot, which is this discrete, the graph with jumps, and then the theoretical cumulative distribution function, or CDF, for the normal that has the same mean and standard deviation as the data. And so what we're doing here is looking for deviations of the plots that we're constructing from the PDF of the normal distribution, the CDF, and other kinds of theoretical lines or curves that would go along with a normal distribution. And so we can see here that for samples of size 5, again, this histogram is very sparse, and so it really does not look too much like that curve, but with such a small sample size, we really would not expect that. Now, every cumulative distribution function is going to be some kind of an S-shaped curve, all right? And so what we're looking for when we look at the CDF and compare the empirical CDF to the theoretical CDF, we're looking for deviations from that theoretical CDF to be an indicator of non-normality of the data. And so we can see here that, there's a fair amount of agreement, I would say, especially given that we have a sample of size 5. This empirical CDF really does not look too much different than the theoretical CDF. And it's probably easier to tell based on whether or not the data would be normal or not normal using the CDF than it would using the histogram. Okay, then we have our probability plot. And when you ask for a probability plot in SAS, it's going to construct a plot like this. And it's based on constructing or comparing or plotting the empirical percentage points from the data versus the percentage points from the appropriate normal distribution. And let me just point out here that the way that SAS constructs their probability plots, this graph is similar to the probability plots, normal probability plots given in the book and in the slides, but they are flipped about the equiangular line. And so in the book, the normal percentiles would be on the vertical axis, and the values for the variate would be on the horizontal axis. And so this is going to be, you'll just need to keep that in mind when if you're trying to interpret a normal probability plot, because different looks of probability plots can give us information about whether the underlying distribution or the data is coming from a let's say a light-tailed table, a light-tailed distribution, a heavy-tailed distribution, whether it's skewed or symmetric. And so if you're going to use the descriptions in the book, you need to keep in mind that those graphs are flipped relative to these graphs. Now, if I scroll down a little bit more, then I get this what's called a PP plot, which is related, okay, to the probability plot that we saw up here. And notice that this PP plot has the cumulative distribution of X on the vertical axis here. And it's got the normal values here on the horizontal. And so, but it also has this, they've got this line superimposed. And this is very helpful because if the data come from a normal distribution, then for both a normal probability plot and a PP plot, then the data will fall close to a straight line. Okay, and so for this example here, using this graph, we know that the data are normally distributed. And so, but we see that the points don't fall perfectly on this line. And looking up the probability plot, we see that those points do not fall perfectly on a line. And so we know, at least for small samples, we maybe should not expect the residuals to fall perfectly on a straight line. All right, so that's something to keep in mind. Now let's look at sample 2, still looking at samples of size 5, and we get a little bit different look and with this data. And so, and we can see here that this empirical CDF maybe doesn't match that theoretical CDF quite as well. If we look at the probability plot, boy, that certainly does not look linear, does it? And if we look at the PP plot, then we get a similar kind of picture. All right, you know, it really does not look like the data fall very close to that line. But again, you know, the sample size is only 5. And then looking at the third sample, we see here that, well, maybe that histogram is a little bit closer to the normal PDF. And that empirical CDF certainly looks better than the second one did. And those points do look like they're falling along a line a little bit better. And those actually look a little, they're above the line. And so the takeaway here is that there's going to be variability from one sample to another. Residual plots are not always going to look the same, even when even if the residuals are normally distributed. And so we need to keep that in mind. And the other thing is that when samples are small, then the points may not, on a normal probability plot, may not fall real close to that line. Now, the reason I included not only the probability plots, but the histogram and the empirical CDF is that even when the data are normally distributed, it can be difficult. Let me scroll back up here. It can be difficult to really have a strong conclusion about whether or not a given data set comes from a normal distribution. And this might be a good example of that. And the reason is we're trying to compare two curves, you know, and so when you're trying to compare curves and look for deviations of the curves from one another, that can be difficult. It's much easier when we're evaluating things visually to detect nonlinearity. And so that's why the probability plots are so useful, because what we're doing here is looking for deviations from linearity. Okay, next we look at samples of size 10. And I'll just scroll through here real quick. And I think we're seeing perhaps a little bit better fit to the normal, the theoretical normal CDF with the empirical CDF, at least for this sample. But we still see that the data points don't fall perfectly on that line. All right, so this is sample 2. And again, I'm just scrolling through here, and you can see here, that certainly doesn't look like it follows the line very well, does it? And then sample 3, and we can see here that even with samples of size 10, there seems to be a lot of deviation from that theoretical line, even though we know that the data have come from a normal distribution. Now let's look at samples of size 25. And this is the sample size used in the example we've been looking at with the delivery time data. And so the histogram here actually looks like it fits that normal curve pretty well. In addition, the empirical CDF follows that theoretical normal CDF very closely. And the points look to fall pretty close to that theoretical line for the PP plot. Okay. All right, and so we see here that as we're looking at a larger sample, we're seeing that at least for sample 1 here, that there seems to be a fair amount of agreement between the random variables and that theoretical line. And in the context of a regression and a residual analysis, these would be the residuals. Okay, here we have sample 2, and there's all, again, seems to be pretty good agreement between the random variables and the line here. And then sample 3. All right, and this one, there's a little bit more deviation. So again, this is pointing out that there's going to be variability from one sample to another. And we may, even when the residuals are in fact normally distributed, that there very well may be deviation from that theoretical line. Now let's jump up to samples of size 50. Now notice in this case that the histogram is left skewed. Even for a sample size of 50, we see that skewness. But it doesn't, apparently it's not too bad because the empirical CDF matches up pretty closely with the theoretical CDF. All right, and the points do tend to fall pretty close to that theoretical line. All right, now let's continue on looking at sample 2. All right, and there's pretty good agreement there. All right, and so I think we're seeing that as we increase that sample size, then the normal variates do tend to fall closer to that theoretical line on the probability plot. Okay, now we're looking at samples of size 75, and we can see that we're getting a pretty good agreement between the empirical CDF and the theoretical CDF, and the points fall close to that theoretical line. Here we look at sample 2, and we get the same kind of result. All right. And then sample 3, still at n equal to 75. And there seems to be more consistency from one sample to another in terms of how these plots look and how they conform to the theoretical distribution. And then finally, well, now actually we've got 2 more sample sizes to go, samples of size 100 here. And so we see a little bit of deviation here from that, from the theoretical CDF. All right, so we can still get that kind of variability that even with samples of size 100. Here we have sample 2, it's sample size 100. And there's good agreement there between the empirical and theoretical CDF. All right, and those points do fall very close to that theoretical line. Sample 3. All right, and we see there's pretty good agreement. And then finally, samples of size 500. And we see here that histogram follows that normal curve very closely, as does the empirical CDF. And then if we look at these probability plots, then we see that there's not much deviation from that theoretical line, much at all. For samples of size 2, it looks like we're getting the same kind of consistent result here. All right, so with samples, with really large samples of size 500, okay, I think we can expect for the normal probability plot to show the residuals really, really close to that theoretical line. And then finally, sample 3 for n equal to 500, again, we get good agreement. So we're getting very good consistency in how these plots look as the sample size increases. So if you've got really large samples, then we can, if the residuals are going to, if they're normally distributed, then we can expect them to be very close to that line that is produced by the probability plot, normal probability plot. And if we see deviations from the points from the line, then we can, suspect that there may be some non-normality. But again, going back up here to the smaller sample sizes, it can be difficult to to identify non-normality and be confident about that when we've got the smaller sample sizes, just because we don't have enough data in a given sample, right, to really calculate those empirical CDF values closely. And the other thing is that there's going to be a lot of variability from one sample to another. So let's go back over to the slides. And so here we see how we can use normal probability plots to make an assessment as to whether we think the residuals are in fact normally distributed, or if there's a violation of normality in some way. And we can also use them to get some specific information about if the residuals are coming from a distribution that is in fact not normal. Is it a heavy tail distribution, a light tail distribution? Is that distribution positively skewed, or is it negatively skewed? So graph A here, plot A, shows the situation when the residuals are in fact coming from a normal distribution. And again, if we've got a very small sample, then we would probably expect more deviation from a theoretical line that's shown here. But for large samples, there would probably be good agreement. On the other hand, plot B shows what happens when you have if the residuals come from a heavy tail distribution, and in particular, a distribution that has heavier tails than the normal distribution. And so you can see here that there's pretty good agreement here in the middle range of the residual values, but for the smaller residual values and the larger residual values, we see that there's deviation from the line in this way. On the other hand, if you've got a light tail distribution from which the residuals come, then you have a similar kind of situation, but the points deviate from the line differently in the opposite way than they did with the heavy tail distribution. If you've got a positively skewed distribution from which the residuals come, or from which the error terms come, then the residual plot would look something like this, where it kind of curves up in the upper ranges of the residual values. And if you've got a negatively skewed distribution from which the error terms come, then the residuals would exhibit this kind of behavior relative to that theoretical curve. Now, keep in mind that, again, the normal probability plot produced by SAS reverses the axes, and so you would need to flip these graphs if you're looking at those graphs in SAS. All right, so in this slide, we're seeing two different residual plots. We've got on the first plot, plot A, the residual plot is constructed using what we would call the raw residuals. And in the plot on the right, plot B, it's using studentized residuals. And again, we would call these internally studentized residuals. And you can see that they have the same basic shape. The only difference would be the scale on the horizontal axis. All right. And so when we're looking at these things visually, oftentimes the different kinds of residual plots, or these normal probability plots using different kinds of residuals, will give us similar information. But keep in mind that you can construct the residual plots using raw residuals, the internally studentized residuals, the externally studentized residuals, which are called the R-student residuals, and so forth. And it just depends on the software you're using, which kind of residuals they're using in constructing these normal probability plots. Now, the next kind of residual plot is constructed by plotting the residuals against either the fitted values, the y-hat values, or the regressors in the model. You could also fit the residuals against regressors that you have data for but have not included in the model. So let's think about each of these in turn. So if we plot the residuals against the fitted values, the y-hat values, or against the regressors, then we can use that type of plot to check for violations of the constant variance assumption. And we can also use that kind of a plot to identify situations where we have not included the explanatory variable in the appropriate way. For example, maybe we've only included a linear component when it actually needs both a linear component and a quadratic component. Now, if we plot the residuals against regressors not in the model, then if a plot appears in that plot, I'm sorry, if a pattern appears in the plot, then that could indicate that that variable, that explanatory variable, should be included in the model, because if it actually is impacting the response, but we've not accounted for it, then that relationship, that effect, because it's not being accounted for, will show up in the residuals. All right, and so that is why it can be helpful to identify plot the residuals against explanatory variables that you have data for, but you've not included in the model. And then finally, you can construct plots of residuals against time order if you know the order in which the data were collected. And that's useful if you're trying to, or in order to identify lack of independence of the error terms. All right, and so if there's a pattern in that kind of a plot, again, the residuals versus time or order of measurement, then that can indicate, if there's a correlation there, then that would indicate that the error terms are not independent. And so here's what a plot of the residuals versus the fitted values, the y-hat values, might look like. And the first plot, plot A, this shows the ideal situation, right? This would indicate that the residuals, the error terms, are appear to be random, all right? And there's no pattern in the data. And you can see here that the amount of variability in the vertical direction does not change as we move to the right, all right? And so there appears to be constant variance. On the other hand, plot B, we see that as we move to the right, and again, the horizontal axis is the fitted value. And so as the fitted values increase, so does the amount of variation in the residuals. And so this would be a good indication that the constant variance assumption is not true. All right, that the variability of the residuals and therefore the variability of the error terms increases as the value of the response increases. Graph C is also an indication of non-constant variance. This would indicate that for smaller values of your response or fitted value, or larger values of the fitted value, you've got less variability in the residuals, but for fitted values in the middle of its range, you've got more variability. And so this is another way that you can have non-constant variance. Now, you could also have a funnel shape where as you go to the right, the funnel gets narrower. It's perhaps less common, but you could have that. And that would also be an example of non-constant variance. And then finally, if we look at plot D, okay, this shows us, so this would indicate that there is a variable that needs to be included in the model, and in particular, a quadratic term of one of the variables that needs to be included in the model. And it's because it's not included in the model, that quadratic impact, that quadratic relationship is not being accounted for. And since it's not being accounted for, it's showing up in the residuals. And so we can see here that by using this type of residual plot, we can detect various kinds of issues, various kinds of violations the assumptions. We can identify non-constant variance, and we can identify when we don't have variables in the model that need to be in the model. And so here are the some residual plots for the delivery time data. This is example 4.4 in the text. And we're going to look at this in SAS, so we're not going to spend too much time looking at it here. But we have two different kinds of plots. First, the one on the left, these are the raw residuals, and the graph on the right would be the studentized residuals. And one of the benefits of using the studentized residuals is that it makes it easier to identify potential outliers. And I would think that this point up here that I'm circling would be a potential outlier. And it's easier really to make that determination with using the studentized residuals than it is with the raw residuals, because the raw residuals, again, have not been standardized in any way. And so it's difficult to know whether a value of close to 7.5 for that residual is large or not. But once we've standardized and in fact studentized the residuals, we know that if we see values of the residuals that are beyond say 3, then those are values that are outliers and they need to be looked at. Okay, and then in this plot, we have plot of the residuals versus the regressors for the delivery time data. And we don't see, so in this first graph, the horizontal axis is x1, the number of cases. In the second graph, the horizontal axis is x2, the distance walked by the delivery person. And we really don't see too much of a pattern in either of these. And so it does not appear that we would need to include higher order terms for either of those variables. Now, this is not from the example, all right? This is just, this shows, this is an illustration of what can happen if we plot residuals in time sequence and we see a pattern. Now, when we plot the residuals in time sequence, if the error terms are stochastically independent, then what we ought to see is something like this from figure 4.3, where we just have a random scattering of points about that horizontal line. But if we see something like this, either of these two graphs, then if we see graph A, what this would indicate is that there's a positive autocorrelation amongst the residuals and amongst the error terms. And if the error terms are correlated, then they're certainly not stochastically independent. On the other hand, when we have a graph that looks like this, where it's constantly bouncing back and forth across that 0 line, then that would be an indication of negative autocorrelation. And again, that would imply that they're not stochastically independent. And so this is how we can identify lack of independence in the error terms.